and welcome to the compile time configuration presentation for RIOT. Basically, the idea of this presentation is to show what's the work so far of the configuration task force. So let's go to it. The agenda is to show the analysis that we did of the current situation, the current state in RIOT of the compile time configurations. Then with that, we came up with a list of requirements that we think are necessary for our configuration system. And based on that, we have a proposal to present with some demos and show you why that proposal fulfills the requirements that we stated before. Okay, so let's start with the current state in RIOT. Commonly, configurations of modules and other devices are passed using macros. These macros are usually overwritten in make files, either the application or different parts of the system, or can be overwritten also using cflags, like this example where we see we can set buffer size and packet buff when we are compiling. Also, these check-ins of values and the logic between the configuration options are handled using the C preprocessor. Another part, board configuration, meaning clocks, peripherals, boot time configurations, and ping configurations, are defined in the perfconf header files. Usually also external devices such as radios, sensors, and actuators are configured using the param header files and can be overwritten per board in the board header files. So having this in mind, what's the current issue? So many configurations and parameters are not actually validated. That means that it can take illegal configurations. It's also quite hard to describe interdependencies between configuration options using just C preprocessor logic. There is a lack of conditional exposure of parameters, meaning that user shouldn't be exposed to a lot of configurations, or a lot of parameters are not actually configuration, but just boot time and hardware description. Finally, it's not easy configurations for a particular build in RIOT. If we see the perfconf header files, it looks like there is a lot of CPU specific knowledge that it's needed to specify the boot time configuration of peripherals such as UARTs, SPIs, I2C, and others, which shouldn't be repeated between boards. That brings copy-paste errors and needs a lot of knowledge from the user from low-level aspects that shouldn't be needed for a board porting. Also, there are few checks in hardware valid configurations using this method. Based on the issues that we found with the current state of configurations, we came up with a requirements list. First, configuration options should only be exposed when it makes sense to be. So the user should only see options that he can configure in a given context. Also, configuration values should be checked, meaning that configurations legal, and conditional default values and interdependency logic for these configuration options should be also available. It should be also easy to get the apply configurations when you're building RIOT in an easy way. You should be able to reuse configurations among similar hardware so you don't repeat yourself in header files, and you should expose only what's relevant to the user. With that list of requirements in mind, we propose the following approach. Kconfig is a language used mainly for the configuration of the Linux kernel. Together with tools, it's used to configure software. From the point of view of the requirements, it solves the exposure of parameters, the restrictions, and the dependency between them. Most of the reference tools are maintained by the kernel community in the repository, and it has proven to work for many years now. Some features of kconfig include conditional and dynamic handling of default values for configuration options, restrictions like ranges, choices, and type for the configuration options, including validation of their parameters. Commonly, the output is a header file and optionally a configuration file which has makes index and can be used afterwards by the build system to select which modules are being built. How can we use this in Riot? Let's see some examples of applying this kconfig to the configurations. Here we can see snippet of kconfig for the gcoop module. Here it defines kconfig module gcoop that can be enabled. That means that we can optionally use kconfig to configure this module. Here, when the symbol is selected, we can access a menu of buffer sizes, for instance, where we can configure the PDU buffer size, the request option buffer, together with their default values, their type, their prompt strings, and their help strings. When we see the menu config interface for this kconfig file that we just saw, we can see something like that. So menus display like this, buffer sizes, observe options, and timeout, for instance. And each of the configuration options show their prompt string, and optionally we can display the help string for the user. In this other example, we can see how the nib module of GNC can be configured. Here, the number of entries in nib is being exposed as a configuration option, which has different default values depending on which modules are being included in the build and which other symbols are being selected. Another feature of this is that we can generate documentation based on the kconfig files. For instance, here we can see an example, a proof of concept of how a Doxygen page of RIOT could look like for the already model configurations, in this case gcoop. We can see the different symbols with their types, default values, help strings, prompt strings, and the dependencies between them. This is very handy because we shouldn't have to uh, group all the configurations in the group manually as we're doing right now in the Doxygen config group. We propose that the integration with the build system of kconfig should be opt-in in the first phase, allowing to configure RIOT as usual, just with the default values in header files, and explicitly enable kconfig for a certain module when a user wants to configure that module using kconfig. Also, a progressive adoption can be the approach because there is no need to migrate all the modules at once. We can just start exposing configurations in kconfig files per module. In this first phase, dependencies are still being resolved by the build system using the use module variable. The generated artifacts are going to reside in the bin folder of the application, meaning that they can go away with a make clean, but the user can choose to save their actual configurations in a file if he wants to. The kconfig file structure will mirror the current file structure in RIOT, so mostly all modules will have their own kconfig file in the same folder. So how would things look like after migrating? Well, kconfig will allow to select the needle modules and solve their dependencies. So we have to create, to model all these dependencies in kconfig files. Modules can be configured using kconfig yeah, through their different interfaces, either menu config, GUI config, or directly writing the configuration files. Tools after can be built on top of this, for example, web visualizations. At the first moment, we thought that hardware can be also configured using kconfig, but there are some reasons not to do this. First, it's not really scalable. There is a lot of code duplication if you want to express the hardware configuration using kconfig files. It would expose too much information that the user shouldn't really see, which is the actual current case in the perfconf header files. It has been already tried by other OSs and has failed because it doesn't really scale. It's not meant for hardware description. It's only for software configuration. So the proposed solution for this part has been around for many years now, and Jose will tell you about that.
So, hello everybody. I want to show here what we think could be a good approach for handling the device device configuration. So this is the device tree. It's a data structure that is used to describe multi-platform hardware. It's standardized. There's already a specification that keeps growing, and there's some efforts to try to use it as the way of describing hardware configuration. And it's also OS agnostic. This data structure just contains information about the hardware, but it's up to the OS to decide what you do with this information. And said is broadly used and developed, which is a known tool, so which is quite nice. So how does this work? The hardware is described using the DTS language, device tree source files. So basically a device is defined by a tree of nodes. For instance, what node could be a system on chip that describes that contains a CPU node. The CPU might have some peripherals, external devices, or whatever. Of course, each node has a set of properties that make it unique, and each node may have children. So here's an example that shows actually two device trees. I'm showing here these both in green are the root nodes. For instance, in this case, we have a Nucleo L452RE that includes a STM32L452RE CPU model. This CPU model will include the STM32L4 family, and as we can see here on the other side of the picture, this Nucleo L476RG has its own CPU model, but they both include the same CPU family. So here you can see how you can reuse. You write once this STM32L4 family, and then whatever CPU model that uses this CPU family is just a matter of pointing it to the right direction. And of course, this can override some information about this one, so that makes it extremely flexible. And on the definition of the STM32L4, we have, for instance, a definition for the USART1, SPI1, and other OSs. Other peripherals. But the nice thing here is we define them once, and then we have our representation of the hardware. So these DTS files can include other files. So that's what I show in this picture. It's possible to reuse. We can also reuse our own node definition, but we can also use definitions from other people. For instance, we could base on some Linux nodes that they describe for their hardware. So it's, I think it's also very nice to be able to do that. And as shown a little bit before, it's possible to override previously defined functionalities from the root nodes. For instance, we can change properties of the other nodes. As we see here, for instance, this STM32L452RE, of course, it has some properties that make it unique. So we can define these properties here, but we still inherit all the stuff defined from this layer. And we can also add new nodes if we have a system on chip. We can, for instance, add a radio that goes in this system on chip, and then we don't have to touch any perif file or whatever. So that's very nice about the language. So let's see it in action. Okay, so I want to show what's possible to do if we have the hardware configuration for some microcontrollers in a device tree structure. Here we are in a branch that contains the device tree for some of the STM32 microcontrollers. Here we are in the default example of RIOT. And if we have all the information in device tree files, we can, for instance, generate the perif.conf file that can, this header of course can be included and used from RIOT. Since we have all this information somewhere in the device tree, then here we can easily generate it via templates. And of course, if we make some change to the device tree structure, we will see it reflected here. So then we don't have to rewrite these files for each time we want to add a new hardware. And since we also have information about the pinouts, we can do some really interesting stuff. For instance, we could print the pinout for a given platform. Print pinout. So here we can see an example on how we can see the configurations or the pinout configuration for the given board. Here we have, for instance, the UART0, XTX go on these pins here, and this, of course, can be really useful information, especially for newcomers into RIOT. And even we can fill in templates to provide, for instance, pictures with the pinout. For instance, let's check this command here, board pinout. So this is generating an SVG file. I will show how this looks like on a Summer 21 because it has a very pretty picture. So board.svg. So if I open this one, we can see that it looks like this. So here's exactly the same information we had before, but of course a more beautiful way and more easy to read. This is just a standard SVG file that gets replaced with some labels by the device tree utility we wrote. So let's see how this works. Let's see how the root DTS file for the Nucleo L152RE looks like. So this is a standard DTS file. This is our root file set. Here we can see we can use C preprocessor directives. So here we are including the STM32L152RE CPU model that will contain the whole definition for our CPU of this board. And then we can see here this is a way to describe how to include or how to add certain perifs to RIOT. So here we are saying that we are using one SPI, one I2C, and two UARTs, and enabling the ADC as well. And here, for using this perif, we need to define a pin controller that describes what's the pin configuration for the SPI, what's the pin configuration of the UARTs. So here's what we have here. I'm not going to go into much details, but just to show how it looks like. And the idea is we define the pin control, the pins here. For instance, we say that for the first UART, the RX pin will be the GPIO A 15, and we use this for the alternate function. And here we have all the nodes of the perf that we are overriding. We are saying that each one should be enabled, so we set the status to OK. And we assign the pin controller we have defined before. So then if we go to the CPU, this include the TSI file that I think is here. Here we can see that we are defining what peripherals are available on this CPU model. This is what we have here. And then we include the STM32L1 family. This compatible, I'm not going to go into much details, but the idea is you can use that for deciding which modules to compile. In Linux, is used for trying to do device discovery. So if we go to the CPU family, so this is the definition. we use this if-defs here to decide if we have to include the node or not. And this is how it looks like. As you can see, these are the parameters needed for standard UART in RIOT. As you can see, all the devices, all the nodes start with status disabled, so that's why we have to enable them on the root DTS file, so then we can know which perfs are available. So yeah, this is ideas. This is how we describe the hardware. Currently, we have these fields here on the perf.conf file, but as you can see, we can describe everything here and then extract it somehow to generate the perf.conf file. Okay, so the idea is to get these DTS files compiled into device tree binary files. So we can flatten the device tree structure into this blob file that contains all the information, but in a compact way. And for doing this, first we run the C preprocessor, so we can process all the includes, define labels, and then we can run the device tree compiler that generates this .dgb file, which holds all the information that describes the hardware. In Linux, we use that file for getting the whole device information on runtime. Of course, we wouldn't like to do that on RIOT because that means that we would need to copy this whole blob in the binary, which is something we don't want. But of course, we can extract the information from there, so we can generate, as shown before, perf.conf files or documentations or whatever we want. So I said before that the device tree is solely data structure, but it says almost nothing about what we should write on each node, what kind of properties they have in order to describe the hardware. And that's what we call bindings. These are a set of usage conventions. For instance, if we go back to our example of the STM32L1, here we have some bindings for the SPI. For instance, we said that we need to define the RCC, the TX and RX DMA. Probably for other perif, we would say that, well, this is how we describe a DMA. The square C, they have this kind of parameters. That is what we can see now on a perf.conf file. But basically, the binding for the GPIO could be that all the GPIO have to have these properties. And so this is what I describe here. Basically, on Linux, what they do is to have these documentation files. For instance, uh, this is the binding for the AG86RF230 radio. They explain like the required properties, but this is only like a convention that says if you want to write the device tree for this device, you would do this. And here they have bindings for all the components. And for instance, if I open just one randomly, yeah, they describe just with documentation, which of course is nice, but there are other techniques that can be used for generate these bindings. For instance, on Sapphire, they use YAML files for describing them, and they use tools that helps to validate what you write on the bindings. And also it's possible to use, for instance, Python classes to describe the schema, so then it's easier to apply validations and whatever we want to do with the data. Okay, so the advantages of device tree. First, it's quite scalable, has been proven on Linux and our system to be quite scalable in the sense of we can describe once the hardware and then we can reuse as much as possible. If there are some minor changes, we can just go and change them in the root file and not having to rewrite each time we want to add new hardware. This is very good for rep boards or shields. It's also quite nice for system on chips. Most of the Nordic radios, they already come embedded with a radio on the same system on chip. So if we already have the CPU and we have the radios, then we can define what a sock is without having to write a complex file. Also what is really nice is we can write the hardware description in a way that if we change the structures that tells Riot how to configure the hardware, we don't have to touch the device tree files. So the information is always there. We can consume the information. We can write another format of perifconf. We can change the documentation, but we only write once this file, which is quite nice. Of course, there are some pitfalls. First, we are aware that if we like this approach, we will need to write the TS file for every CPU family, for every board, for every device driver, which of course is something that might take time, although it's possible to reuse stuff from Linux, from other OSs, but still we need to write these files. It's only once, but this could take some time. The second problem is that device tree was made for using the device tree binary blob directly, but since we cannot do that, we have to parse it, and that means that we have to add some kind of custom tools. But there are some very good Python tools for parsing this device tree blob file. So at least we have a very nice way to traverse this DTB file with standard Python tools that are not maintained by us. And of course, the migration would take some time. So we would need to maybe design a way to on how to integrate the device tree so we don't break Riot, and we can also like continue adding more boards and more platforms. But of course, this would take some time.
Once we have the described hardware and the boot time configuration for it, we can use that information to feed into the kconfig configuration system. That means that device tree declare which hardware we have and are using, and kconfig will expose the software configurations for that hardware that we are using. That we can selectively show or not show which modules depending on the hardware that we have. So if we declare having a radio on the device tree, kconfig will show up the possibility of enabling the driver for the supported radio on the hardware. Also, it will show any configurations of that software piece. So how could it look after migration? Well, as Jose showed, we could generate the board pinout information based on the hardware configuration that we have in the device tree. We can also check pin conflicts and other types of invalid configurations in the hardware. And we could generate the perifconf header files based on the device tree descriptions. Also, we could have the source device tree and the generated perifconf upstream, meaning that we don't have to run and recompile the device tree every time, just only when the device tree is changed.